Welcome to my ozone technology course. This will be session 25A, ozone in cooling towers. This session will discuss on installation of ozone in schematics and chemical costs involved. In order to ensure sufficient ozonation, the specification of the ozone generator must be take the following into consideration. The total volume of water in the circulation including pipes and chillers, the flow rate of the cooling water, contact time, exposure of ozone to the cooling tower water, the cooling capacity of the system, the location of the ozone generator, the distance between the ozone generator and the application of ozone to the water, the compressor air feed pressure, water and oil content, then the concentration of ozone in the system. Chemical companies always raise the issue of ozone causing more corrosion with chemicals. Those who believe this can rest assured that even with corrosion inhibitors, the cost of ozonation is far less than the cost of chemicals, and the return of investment is still far less than 6 months of installation. Corrosion is more due to electrochemical reactions because of the presence of chlorine in the cooling tower system rather than the ozone. We try to use the sacrificial anodes or countercurrent distribution system to reduce this electrochemical corrosion, and no amount of inhibitors etc. will be able to reduce it. This slide represents a diagrammatic representation of the application of ozone in cooling tower water. Most important thing is having specified what ozone generator to be used, how much of ozone is to be installed, and knowing the volume of the circulation water, etc. The compressed air that is normally within the area in most of these cooling tower installations, etc., will have compressed air for refrigeration systems and use of valves, closing and shutting down of valves. The compressed air must be oil and water free. So you have a good oil and water filter, and this compressed air, at least 150 psi, is passed through the ozone generator. The ozone generator, the air that is converted into ozone will be drawn out and pushed out by the ozone generator into the venturi. There is a separate section where the water is taken out of the sump and through a secondary pump, and that goes through a contact chamber and then back into the cooling tower water tank. The contact chamber gives sufficient contact time for the ozone gas to be distributed and dissolved, and by the time it arrives out of the contact chamber, most of the ozone would have dissolved in the water. This dissolved ozone is now pushed into the water circulation. You can have a meter, dissolved ozone meter, or a redox meter to indicate to you the quantity of ozone that has been injected into the system. Now, this water full of ozone goes from the sump back to the heat exchanger, it will now be exposed to all the parts of the heat exchanger and come back from the heat exchanger to the top of the cooling tower. You will notice that the temperature of that water is at about 45 degrees centigrade. It is where most of the ozone would have already been dissipated, and there will not be any ozone coming here, but the water will be of a good quality. Now, when the suction fan goes on, the air that is sucked from the sides of the tower will also cool the falling water spray, and as well as some of the moisture or atomized water can be drawn out into the air plume which goes out of the tower. You will note that this, because of the water that is coming in at 45 degrees, is without ozone, plus of very good quality, that is without bacteria, virus, etc. So any atomized water that is going into the plume is guaranteed to be sterile or bacteria free or Legionella free. It is important, it will be useful to use a secondary pump simply because we don't want to try to get and interfere with the main working pump, and we want to make sure that the flow rate is sufficient and cooling tower contact chamber, the ozone in the contact chamber is sufficiently slow enough, the flow rate is slow enough to ensure that most of the ozone has been dissolved and goes back into the water tank. Of course, when you use ozonation, it has got several properties like descaling properties, and the scales will be distributed from the chillers, etc., in the pipes back into the water tank. It generally sinks because of its heavy, and goes back into the sump. It is possible for us to introduce a sand filter or some sort of filter to filter off and put it back into the water tank, so that we reduce our erosion corrosion on the system. This is the top view of the ozone treatment system. As you say, the air compressor gives a compressed air, oil-free and moisture-free, back into the venturi. The ozone water pump draws out from the tank back into the contact chamber. Ozone goes through the venturi, mixes well. You may have an ozone destructor so that we don't get ozone seepage into the atmosphere, and the ozonated water goes back into the tank, and from there it goes straight to the heat exchanger or the rest of the circulation system. The hot water comes in from the heat exchanger on the top. There is a raw water input, top up, and there is a blow down where you can reduce the water levels, reduce the TDS by blowing out some water and topping up with raw water to make up the volume loss, normally also through not only through blowdown but also through the evaporation and water sprays, etc., that may also lead to reduction in the volume of water in the circulation. So this is a top view and this is a side view. This photograph represents the chiller tube after removal of the chiller plates. This is a typical example of an ozone installation where the tubes were, after it has been cleaned up, etc., before the installation, and after the installation you can see the pipes, the tubes, etc., extremely clean after the period as shown in the photographs. The photographs in the picture also shows the tubes after the chiller plate has been removed. This was done in an existing cooling tower system prior to the installation of ozone. If you notice, all the blockages which had occurred prior to the installation, and this was cleaned up and ozone was installed, and 1 year from the installation the chillers were opened up for the annual maintenance, and this is what you find, and you see how clean the tubes are compared to the tubes that are found when prior to the installation of the cooling tower. So because there is no blockages, the flow of the water is not impeded, and there is no necessity of using brushes or rods, etc., to draw out or clean the chiller tubes of rust and scaling. This is a picture of the chiller plates, and if you notice that there is a sacrificial anode which has been installed here, the end plates, so that they can reduce the amount of corrosion in the system. This was before the ozone was installed, and this is after the ozone was installed. Obviously, these are all parts of the system that cannot be removed. But if you notice that all these areas were without rust, and there's not much of scale building up in the end plates. We shall now go into the principle of application. Ozone is produced as a gas using either air or oxygen as a feed gas. Of course, we get more ozone if we use oxygen. The concentration of ozone can be between 1 and 12%, depending on the ozone generators. However, it is never necessary for us to have such a 12% concentration for the application of ozone in cooling towers. Even if we have of about effective concentration of ozone in the cooling tower water of 0.1 ppm or 0.2 ppm will be more than enough. If air is used as a feed gas, the ozone output depends upon the dryness, and it becomes maximum when the feed gas is below the humidity of the feed gas is below minus 48 degrees centigrade. The ozone air or ozone oxygen mixture must be diffused into the water. The rate of transfer depends on the surface area of the gas and the contact time and concentration. The higher the surface area and the longer the contact time, the lower the water flow rate, the greater the diffusion. Contact time is increased in the contact chamber with the application of the contact chamber. Why biocides are not necessary if you use ozone? As ozone is more than 3,500 times more effective than chlorine using the standard E. coli test, and chlorine is superior to normal biocides, except that it is corrosive. Ozone at a concentration of 0.01 to 0.02 ppm would ensure that the bacterial level, considering it is an open system, is below 1000 CFU per mil. Legionella below 10 CFU per 100 mil, and pathogens as nil. The requirement for cooling tower water is the above. In fact, the bacterial count is below 100 CFU if you use ozone, considering the requirement of 1000 CFU. And Legionella will be 0, even though permitted levels are below 10. Why are scaling inhibitors not necessary? Ozone has the following effects. It prevents slime formation. Ozone reacts with all the organic sediments, flocculates organic colloidal solutions to sediments, and kills bacteria that attach to the slime and prevents seeding. That results in the formation of scales. Removal of existing scales. This is very important. Ozone attacks the bacteria and slime that form the scale, and the scales do not have any more skeletal surface for the maintenance of the scale, because it is important that the organic material or slime is a basis for the scale to cling together. And once the slime is removed, the scales cannot cling together and onto the surface of the pipes, and they break down into particles and settle in the tank. In other words, they break down the particles in the pipes and are pushed back into the tank, and being very heavy, it settles on the sump, near the sump, which can be taken out through a filter. All that is required is sweeping of the scale deposit and the sediments on the floor. Alternatively, a filtration system can be installed that will spontaneously collect all the scale. Why anti-foam agents are not necessary? Foaming is generally the result of organic colloidal solutions present in the water, and that is churned by the rapid flow of the water. Ozonation destroys or flocculates organic material so that the cooling tower water does not have any organic material that can cause the foam. So there will be no froth or no foam. so anti-foam agents are not required. If by chance anybody adds any material or any chemicals that contain organic materials or organic chemicals, then the foaming will start to happen until such time the ozone destroys the organic material in the chemicals that is added, and then then the foaming will stop forming. Remember, frothing and foaming is an enemy for energy transfer or heat transfer because it will reduce the contact contact time and contact surface of the water in the chiller tubes, and therefore less heat is transferred from the hot chiller's refrigerant liquid to the cooling system, cooling tower water. Why corrosion inhibitors may be necessary? Chemical companies always accuse ozone as causing corrosion. There are many research articles applying ozone into cooling towers like NASA and GPL, where it has been confirmed corrosion rates are no more than when the towers are treated with chemicals. Corrosion cannot be eliminated. Please note again, the corrosion cannot be eliminated. It can only be reduced. The reason is electrolytic corrosion will always be there because of the presence of chlorides in the water. So there will be no bacterial corrosion if ozone is used because it is killed, bacteria is killed, and there won't be erosion corrosion as the sediments are heavy, collect at the bottom of the basin, and it will not be carried in the pipes, and therefore it can be filtered off. So in order to stop the electrolytic or reduce the electrolytic corrosion, we have to ensure that the chloride levels must be monitored and maintained below 300 ppm. The lower the chloride level in the makeup water, the better it is for the system, and the higher cycles of concentration we can operate. Many people will determine the cycle of concentrations using the TDS. I would normally determine the cycle of concentration using the chloride levels. The chloride levels in the cooling tower water divided by the chloride levels of the feed water. That is more accurate to give the TDS because that is the one that can cause the corrosion. Ozone protects metal surfaces. Just like the chromates that were being used before 1990s. Chromates are very strong oxidizing agents, and they form an oxidative protective layer on the metals and reduces corrosion. The ozone acts in the same manner as chromates. Chromates were originally applied as corrosion inhibitors, but because of its toxicity, it has been banned. As in chemical treatment, either a sacrificial anode or applied counter current to the electrolysis current will have to be installed to reduce the corrosion. Corrosion with ozone is no greater than corrosion with chemicals. The average life of properly treated chemical towers and ozone towers must not be less than 25 years for economic reasons. Corrosion by ozone is still being questioned. Even if it was true, a non-organic biocides non-organic corrosion inhibitors compatible with ozone treatment may be recommended if there is any concern with corrosion. This is a chart which I have drawn out as more as a summary. When you have a bacteria algae problem, if you use ozone, you are going to have very low biocounts. And reduced corrosion, there's no scaling and no foaming. If you have a corrosion issue, you can, if you are really concerned, use inorganic corrosion inhibitors, which is generally not required. But with ozone, there will be much reduced corrosion. There's no scaling, no foaming. If there is a problem in scaling, then with ozone, you will have no scaling. And if there is any scale, those scales will be broken down so that you will have a clean tower system, including the pipes. Foaming, the problem of foaming, which will not exist in ozone-treated towers, but if chemicals are added which contain, for example, organic material, ozone will break it down, but obviously there will be a higher consumption of ozone and it may compromise the bactericidal properties. So it is important that we do not add any chemicals which contain organic materials into our ozone-treated towers. Because of ozonation, you can operate the towers that are very much higher TDS, because once the TDS increases above the saturation point of that particular chemical, that chemical will deposit into as insoluble precipitates and can be removed through filtration. There will be no blowdown required, so you don't lose water because there's no no high TDS to reduce blowdown. But if you have a high TDS because of the chlorine differences, then blowdown will be required. Whether it is ozone or chemicals, you have to reduce the blowdown to reduce the chlorine content to much below 300 ppm. Remember, even the 300 ppm of chlorine in the water will have some detrimental effect on corrosion because of the electrolytic reactions. You don't have to top up water, because the only top up that you use is the loss of through evaporation and drift. The cost for top up water only, which is loss for evaporation and drift, rather than loss because of the high TDS, because of the blowdown. Recalling biocides, organics, they are organics. Continual modification as bacteria develop resistance to older biocides will result in increased cost and top-up addition to rectify loss and blowdown. Scaling inhibitors, top-up addition to rectify loss and blowdown. Corrosion inhibitors top up addition to rectify loss in blowdown. Anti-foam indicator agents top up addition to rectify loss in blowdown. Sacrificial anode and countercurrent to reduce electrical corrosion for both chemical and ozone systems. Feed water intake to maintain circulation water volume after continual blowdown to maintain reasonable TDS. So if you look at the disadvantages using chemicals, and ozone is really the preferable solution. This is the end of session 25A. Thank you very much for having the patience of viewing or listening to my session. The next session 25B will be on the principles of application of ozone to cooling towers, second part. If you are new to this session, please refer to sessions 1 and 2 on the program details and sessions 3 to 24. If you like this presentation, please click the like icon and subscribe icon if you want to be notified of the next session. Thank you and have a very good day.